motion in 2 dimensions, okay? This is projectile motion, and you see this classic shape that you are familiar with, and of a fountain, yeah? Or sparks flying when someone is soldering, or if you throw a ball, it follows this path, the red path. These are all projectile motion, all following this parabolic path. Okay, and this is what we're going to study. This is basically motion in 2 dimensions. So the ball is traveling horizontally like this, and the ball is also traveling vertically like this. Yeah? It's changing height, and it's changing distance along this direction. So we can split the motion into 2 directions, X and Y. And then we can combine them back to get our final position and velocity, etc. Okay? So projectile motion, an object may move both in the X and Y direction simultaneously now in 2 dimensions. This form of 2-dimensional motion, we're going to study a special case, which is projectile motion. Okay, so what constitutes projectile motion? We're going to say the projectile motion always has a parabolic path because the only acceleration is the acceleration due to gravity. Okay, so once the object has been launched, doesn't matter if you give it a certain initial velocity or not, or in which direction you give that initial velocity. Once there's no other force acting on it but gravity, it's going to follow a parabolic path. Okay, and we're going to assume that we can neglect air friction. Okay, you can do this when the object is much more heavy and massive than to be affected by the motion of air. We're also going to ignore the rotation of the Earth. Okay, so you don't need to worry about these for now. Okay. We're going to follow certain rules. We're going to split the motion completely into the X and Y components. Okay, so if we're looking at the X direction, we're going to think about what's happening in the X direction. We're going to think about what's happening in the Y direction. And by definition, our acceleration due to gravity, G, is happening in the Y direction, pulling the object towards the center of the Earth. Yeah? So in the X direction, there is no force. There is nothing pulling it. So there is no acceleration. Okay, so AX, the X component of the acceleration is 0. And it remains 0 throughout that motion. Hence, it's uniform. Remember, to use our kinematic equations, we have to have uniform motion. In the Y direction, again, the acceleration is uniform because it's G. It's negative 9.8 all the time. Okay? If we know the initial launch velocity, we can break it down into its X and Y components. V0x being given by V0 cosine theta 0, which means the initial launch angle. V0y is V0 sine theta V0, sine theta 0, okay? And we'll do problems based on this so that it becomes more clear how to apply these formulae. So let's look at that parabolic path. It's right here, this dashed path. Say a football that you kicked from the ground, it rises up into the air to some maximum height and then comes down. It has a symmetric path either side of its highest point, and it comes back and hits the ground. So these are my 2 directions, the X direction and the Y direction in space. Let's look first at what's happening to the X direction. To the X direction, it launches off with a certain initial velocity V0, which has components V0x along the X direction and V0y along the Y direction. So we're just going to look at V0x. There is no acceleration, which means my V0x must never change. So let's just follow this arrow. We expect it to not change all through the motion. Second position marked here, V0x looks exactly the same. Here, V0x is right under here. You can't see it, but it is marked here. It's exactly the same as this. And V0x here exactly the same, V0x here exactly the same. So indeed, there is no change in the velocity in the X direction. Now let's consider the velocity in the Y direction. So let's look at the Y component of this initial launch velocity. That's going to be v0 sine theta 0, where this is theta 0. That's going to give me this. v0 sine theta 0 is vy. It launches off where here a fairly significant y component. As it goes upward, the velocity or the velocity vector is upwards, the acceleration vector is downwards. They are anti-parallel, so the object is going to be slowing down, and it keeps slowing down till it reaches its highest point. We know this from the free fall that we did before. So we expect the velocity vector to become less in magnitude and keep reducing all along here on points which are not shown until it becomes 0. So Vy at the highest point is 0. And V0x is exactly the same. So our resultant vector here is exactly the same as V0x. Hence, V0x is hidden behind the red resultant because they are overlapping each other, since there is no y component just at this point. As soon as it begins to come down, you now have a negative velocity. Yeah, and now velocity and acceleration are both downwards, so the object starts speeding up downwards. So Vy, look at its velocity, look at its magnitude as you come here. It's much greater. And this is exactly what we expect. So it's going to come down at its fastest velocity and hit the ground. Yeah? And now for each position, its actual velocity is just the sum of the x and the y components. So if you do a vector sum, you can draw a rectangle here. You're going to get this as your algebraic, as your graphical sum. Yeah? Or you can get its magnitude and direction algebraically. But this is the resultant vector of these two components. Similarly, this is the resultant of these two components, slightly less because the y component became less. X stayed the same. And then it becomes the same as the x component because the y becomes 0. And then it's starting to point downwards because now my y component is downwards and x is the same. And then the y component is increasing in the downward direction. So the red arrow is increasing in the downward direction. That tells you the speed, the magnitude of this. Yeah? So do we understand this graph now? It's really important to be able to understand and explain this graph. Okay. It so happens that depending on that initial launch angle, you get different, what I call ranges. Okay, range is the maximum distance along the x-axis. So this is the range from where you launch it to where it hits the ground again. Okay, and this, for the special case where you always launch from the same height that it lands, you find that interesting things happen. So if you launch it at 15 degrees, you get the same range till here, just say about 125, as if you had launched it at 75. So 15 and 75, they give you the same distance in range. And that's, those are complementary angles. Similarly, look at 30. 30 has a much bigger range to 15. And there's another angle coming here, which is 60. 30 and 60, again, complementary angles. That means they add up to 90 degrees. So what happens at 45? 45, you actually get the maximum range. So if you're playing football outside and you want to kick the ball as far on the opposite side as you can, you want to hit it really hard at 45-degree angle. Yeah, that's going to give you a maximum range. Okay, so let's look at some things. What can we say about the motion in the x direction? We already said that the x velocity, the x component, Vx, it never changes. So it's the same as the initial x component. The 0 stands for initial. Time is equal to 0. So V0x is same as Vx. And what is V0x? It's V0, the resultant velocity, cosine of the initial angle. Yeah? And it's constant throughout the motion. These are just dashes. These are not negative signs. Don't get confused. What about the acceleration in that direction? It's always 0 and uniform. Okay? So we have only one operative equation. If we want to know the displacement in the x direction, it's just going to be given by the velocity times the time. Yeah, this is the only operative equation in the x direction. X equals v0x times t. What about the y direction? In the y direction, we have uniform velocity where the acceleration is negative 9.8, okay? It's the value of g, meters per second squared. And v0y, the initial velocity in the y direction is v0 sine theta 0, okay? This reduces to 0 at the top and then starts increasingly becoming negative, okay? So all the kinematic equations apply in the y direction. At any point, if you want to know the resultant velocity, you need to combine the x and the y components of velocity at that point. Okay, so this is how you'll use Pythagorean theorem to combine to get a magnitude of the velocity. And this is what you'll use, the tan inverse of the y component over x component. Remember, it's always y component divided by x component. And you might need to add or subtract 180 here to get the right angle, okay? You have to think about the quadrants like we discussed before to get the right direction for the velocity. So at any point, you're going to have to combine the x and y back together to get the resultant motion. Okay. So in summary, what did we find for projectile motion? It's a special case which we can reduce down to two one-dimensional motions along x and y, and completely different things happen along the x direction. We have no acceleration here, and we have a negative 9.8 meters per second square acceleration here. In both directions, x and y, we have uniform acceleration, so the kinematic equations apply. In the x direction, they just boil down to one equation. In the y direction, all three equations apply for kinematics. Okay? So the projectile motion can be described as a superposition of two independent motions, one along the x direction, one along the y direction. Okay? To solve this kind of problem of projectile motion, you're going to typically start by selecting your coordinate frame. You're going to sketch a diagram. You're going to put on as much information as the problem gives you for the initial and final positions, velocities, accelerations, whatever you know. Okay, remember, some things will be assumed on your part that you need to know what the acceleration is along the x direction and what the acceleration is in the y direction for projectile. You're then going to start by resolving that initial velocity along the x and y components, yeah, into x and y components. You're going to treat them differently. So you're going to follow kinematic equations for horizontal and those for vertical, yeah. And then you're going to try to solve them for whatever is asked for using techniques of problem solving. And then you're going to analyze whether it makes sense, the results that you've got. You might need to go back and have to combine your two x and y directions if they ask you for a resultant velocity. So we're going to do some problems in a minute and become more obvious. Okay, some things which are less obvious but you need to bear in mind. If you get a problem where an object is fired from a moving object, okay? So if this aircraft or this helicopter is moving in this direction at 40 meters per second and an object is thrown out of it, that object starts with this horizontal velocity, okay? So it will not start with a vertical velocity given that this object is moving horizontally. So it's important to bear that in mind. Then there are some special formulae. We're not going to derive them. You're just going to be able to use them. This is for the range. Range equals v0 squared, so initial velocity squared, sine of twice the initial angle, okay, whole divided by g, which is 9.8. Delta y, v0 squared, that's the initial velocity squared, sine squared theta, the initial angle, divided by 2g, okay? And this is the maximum height that it reaches. This one is the maximum range for the object. These apply only when the launch height and the final height are the same. So the ending and starting levels have to be the same. If you throw a ball off a cliff and it lands on the ground, you cannot apply these equations because their starting and ending heights are completely different, okay? So you need to bear that in mind. It's always these assumptions, these caveats that need to be borne in mind in physics. Okay, let's look at some group work. So let's do another problem. Can a goalkeeper at his or her goal kick a soccer ball into the opponent's goal without the ball touching the ground? The distance will be about 95 meters. A goalkeeper can give a ball a speed of about 30 meters per second. So you can sketch this problem out, yeah? You know an initial velocity, you know the total distance. You want your range to be greater than or equal to this, then the answer will be yes. So this is a question about the range. How far can he throw it? And you're going to assume that he throws it at that maximum range angle, which was 45 degrees, right? So you can use the formula that I just showed you for range, delta x equals v0 squared sine 2 theta 0 divided by g. And you're going to use 45 for the initial launch angle, since we already know that gives the maximum range. So twice of 45 is sine of 90, which is going to reduce down to 1. Yeah? We know this initial velocity in the problem. It's given us 30 meters per second. Yeah? So you need to square the whole thing, divided by g, which is 9.8. Just put all this in your calculator, and it's going to give you 91.8 meters. So is this greater than 95? No. So he cannot throw the ball if the maximum speed he can throw it at, initial launch speed is 30, at that 45-degree angle, he cannot reach into 95 meters.